Okay, now we're going to look at the exam question on the method of characteristics from the 2017-18 paper. Okay, this is quite a typical method of characteristics question in that it starts with a description of the San equations and the method of characteristics, and then it follows by a calculation part. Let's just quickly look at the first part. It identifies the San equations and the characteristic form in the and these are given in a pair of equations for the method of characteristics. And then it asks you to describe the significance of a characteristic. Describe what a characteristic is, and you'll have to take this from your notes. Describe what a characteristic is, in that it is a line in space described by this right-hand equation, and that along that line in space and time this equation applies. So it tracks changes in depth and velocity or flow or wave speed, etc. along this characteristic line. Second part of the question says discuss the zone of quiet and the domain of dependence. Now you need to get these clear from your notes, that those define where information is coming from to a particular point in time and space, and how that information, the depth change and velocity changes, and what that can affect upstream or downstream and further forward in time. Okay, so it's a little bit of a description there. We're looking at probably a half page of writing, or a page including some diagrams. You really need to get some diagrams in there as well. That's worth 6 marks. Now the majority of this question you will get 14 marks for doing the calculation. This is a standard calculation, and the next few slides we're going to go over this calculation. So we've got a river channel flowing in uniform conditions. We're going to have to do a uniform flow calculation, and there's a depth increase by 70% due to a release from a reservoir. Now what we want to know is, when that depth increase happens, what will be the flow in the river? The flow, well, we need to calculate that using the method of characteristics, and then we want to know in the second part how long it will take for this depth increase to affect 2 kilometers downstream. Okay, let's get started. So, right, we've got uniform flow conditions. Let me draw a channel with uniform flow. So you've got a slope, sloping channel of 0.002 with a Chesney C equals 50, and we've got uniform flow. So uniform flow, everything's constant, parallel, the surface is parallel to the bed, the depth are all the same, and this is key. We need to use this information in calculating our characteristics equations. So we've got this this Chesney equation for uniform flow. We know that we're going to use this. We're going to calculate the uniform flow depth and actually the uniform flow. There's a little bit of algebra to do, so let's have a look at that algebra. We've got a wide channel. We were told this. We were told the flow per unit width, which was Q. Now let's just check. We've got a wide channel. R, hydraulic mean depth, equals Y. The area, it approximates to a rectangular channel, so area equals by, and Q equals the width times, capital Q equals the width times lowercase q, which is the flow per unit width. So we can put those into our uniform flow equation and get an equation for Q. Note how now we've got Y to Y. I've written Yn because in uniform flow this is normal depth, so we're going to solve for Yn. We'll just rearrange that, put a Q in, which was lowercase q, which was 3, C was 50, S0 is 0.2, giving us 1.216 meters per second. Okay, so we've got normal depth. Now what we know is that the depth is normal here, yn, the depth is normal at any other point, yn, further downstream. It's the same along that. We're going to use that. So we've got an upstream boundary, so we've got a backward characteristic curve. There's our backward characteristic curve. What do we know about that? That curve, that the dx dt is equal to v minus c along that curve. Remember that? Backward characteristic. And along that line applies this discretized characteristic equation. So we were given this in the question, and I've split this up, discretizing it. We're going to calculate this right hand side at this point r. Remember that we've got uniform flow, so in uniform flow S0 equals SF, so this is going to cancel to be 0. That's the important thing. And we know we can calculate CR from the depth, and we can calculate VR. So we can calculate VR by dividing our Q, which is 3, by our normal depth to give us a velocity. We can calculate CR by the square root of G times YN. Okay, and that comes out to be 3.452 meters per second, and the velocity in the channel is 2.467 meters per second. Okay, so we're going to now apply this characteristic equation, substituting our two values here, and the only unknown, we've got a CP. What is a CP? Well, we've been told that the depth increases. The depth increases by 70%, so YP, we know, will be 1.7 times YN, which gives us the depth has increased from 1.216 to 2.067 meters. So CP is root G YP. So CP is going to increase to 4.5 meters per second. Now we need to put these into our characteristic equation, which I've handily rearranged here to give us VP as the subject, and that simply calculates to VP is 4.563. See, we've got supercritical flow there. V is greater than the wave speed. Okay, that's besides the point. And QP, so the flow now, which is what the question asks, is VP times Y. So that's the velocity times the area, but remember this is width per unit width, so the width is 1. So the flow, 9.44, it's not meters per second, that's meters squared, meters cubed per second per meter width of the channel. Okay, remember to get your units right. So we've now got the conditions at P. We've got CP, we've got YP, and we have VP. Now from that point, remember this took 40 mins to 40 mins to change. From that point we've got a forward characteristic. Here's a forward characteristic which along that line dx dt is equal to V plus C, and actually VP plus CP. So we can write that line. We've been given this delta x, it's 2000 meters. What is delta t equal to? Well, that's our challenge. So we've got the equation of that line, that characteristic line. We rearrange that in a discrete form. We know VP and CP. We just put those numbers in. We know delta x is 2000, comes out to be 220 seconds. Sensible numbers, that comes out to be 3 minutes and 42 seconds. Okay, you get to this point, you've got 14 marks.